Okay, so this is a table of Fourier transform properties. It's not comprehensive, but these are the ones that I think are pretty useful. Personally, I would make your own table as a combination of the one that's in Dr. Miller's tutorial notes. Dr. Miller's lecture notes, and also the table from the textbook, which is, I believe, on page 331 in some versions. If not, it's like towards the end of chapter 4 in the textbook. And I would like make a table based on those two. But yeah, these are the properties that I think are pretty important. First one's linearity. So if you apply a Fourier transform on on an addition of two signals, then you can just do it on each signal individually and then add it up. There's a time shift. So if you shift your signal by t naught, then on your Fourier transform will be the original transform of f of t multiplied by this sort of eigenfunction looking thing, except it's e to the j 2 pi f t naught. And you can also do frequency shift. So let's say you have your Fourier transform and you decide to shift it by a frequency f naught, then the corresponding time domain will be like that. So the original f of t, if it wasn't shifted, multiplied by e to the j 2 pi f naught t. You have convolution on time domain and convolution on frequency domain. So convolution on time domain gives you multiplication on frequency domain. Convolution on frequency domain gives you multiplication on time domain. And finally, you have the nth time derivative. If you take the nth derivative on your f of t, you basically just take the original Fourier series and multiply it by j 2 pi f to the power of whatever derivative you're doing. Yeah. They're also common Fourier transform pairs. So if you apply the analysis equation or synthesis equation, you'd be able to show that these pairs do exist. The one you'll probably see most often, though, is for one-side exponential decay, so e to the negative at us of t. And this might look familiar because this is actually the impulse response for your linear first-order differential equation with initial condition that y negative infinity is equal to 0. And its Fourier transform is a fraction, and it's a complex number, 1 over a plus j 2 pi f. Someone answered the survey asking what a sinc function is. So by definition in engineering, a sinc function is just sine of pi x divided by pi x. So when you take a rectangular function, which looks like this, with height a, and let's say it's centered around 0, negative t over 2, t over 2. This t can be any t. Then that's a rectangular function. Your corresponding Fourier series, Fourier transform, is going to be the height of your original rectangle times t, which is really like the length of your rectangle. So this is like actually the area, times sinc of f, sinc of f t. Remember, this is a function of frequency. And and I said that sinc of, let's say, x is is just equal to sine of pi x divided by pi x. So what this really is AT times sine of pi tf over pi tf. Which is what I think I had there. Yeah, or pi ft. I write, remember just f is your actual variable that's changing. Yes?
Question. So for the rectangular function, for that transformation to be true, it has to be centered at 0, right?
Yes.
So then it's not using time shift.
Well, if you time shift it, then you can combine this pair with the property of time shifting. Yeah. Yes?
What does the sync function look like if you were to graph it?
Graph it? Something like this, I believe. Pi. I think like this, actually. Yeah, it looks kind of like a normal distribution, but it's not.
It looks like a sign that like bottoms out. Yeah.
Like this.
Yeah, but it goes down. It goes.
Oh, it goes below. Oh, yeah, actually, great. Yeah, it should go below. Yeah. So, right. So, like, you can think this way. Right. So your sine of whatever looks like this. Right. And then an exponential, so like 1 over something, looks like this. So you combine the two. Actually, Adam, can you Google what a sync function looks like?
Yeah, actually, I think.
OK. Yeah, I thought it.
I don't think you don't really need to know like exactly what it looks like. But I guess if you're curious, I could write it out.
Yeah. Okay.
Yeah, it looks something like that.
Okay. So moving on from that, here's the first example you could do with a Fourier transform table. So why don't we attempt this? Lift this up. Yeah. OK. So why don't you guys take OK, this is there. Why don't you guys take a few minutes to do this example? Once everyone's copied down, I'm going to switch back to the slides with all the properties. Yes?
Just like a general question, how do you know if U of t is supposed to be like US of t, like unit step, or like the input?
Oh, in the textbook, they always use U of t. They mean the unit step. For us, I'm pretty sure we're consistent when we design our midterm questions that they're all going to be US of t.
Okay, so this would
Yeah.
be the input.
Yes. No. Sorry, no. This would be the unit step. Unit step. Yeah. Let's call this entire thing x of t. All right. Like our input is this equation. Yeah. Okay, if everyone has a question copied down, I'm going to go to the properties table. Wait. Which one does it? Yeah. Or the pair table.
Oh wait, there's a function f Oh wait.
Why don't you just have to do like, don't you just have to do this like expanded
Okay, so, oh, I didn't have the solution up. Okay. Simple. Okay, so the first step that we wanted to do this problem is that we'll convert the sign into a complex exponential, because that's easier to work with. So this is still e to the negative at, and this cosine will become 1/2 e to the j 2 pi f naught t us of t plus e to the t half right. Now we want to, simplify by bringing the two exponentials together. So this will be 1/2 e to the negative alpha plus j 2 pi f naught, entire thing times t, us of t, plus 1/2 e to the negative alpha minus j 2 pi f naught t, us of t. So what we have here, the factor in front of t is a complex number, but the real part alpha is negative. And same thing here. We have a complex number where the real part is negative. So we can just use our table. And we can see that in time domain for a negative real part a times us of t, we have the corresponding Fourier transform. And remember, we're using another property here that Fourier transforms are linear. So if there's just a constant, we can just multiply it in front of our Fourier transform. So the first term will be 1/2 times 1 over, this entire thing is our a. So it will be negative alpha plus j 2 pi f naught plus j 2 pi f plus 1/2 times, this part is our a, so there will be negative alpha minus j 2 pi f naught plus j 2 pi f. And that's it. Questions?
Don't you have to switch up the negative a plus j 2 pi f naught because you have to pull out negative t? Or you have to pull out a negative?
Negative alpha is a negative number. We're assuming alpha is positive here.
Right, but then you bring, so like that whole thing is negative alpha.
Oh, he's right.
No.
You take out the negative when you bring it down, right?
So,
The formula for the negative a.
right, okay.
Wouldn't alpha plus j 2 pi f naught become the a?
How do I explain this?
Like that whole thing in front of the t is your negative a. So that is the equation. So then when you bring it down, you have to take out a negative.
Okay, yeah. Yeah, you're right. Okay, so yeah, this should be a plus j 2 pi f naught.
That whole thing is your a. So you pull out a negative out of the whole thing.
All of a sudden, it's a minus.
Yeah, that's fine. I just switched the order.
Oh, okay, yeah.
Yeah. But yeah, okay. Okay, there we go. We're all happy now. Okay, question. Yes.
Hold on. Having that whole term as your a, I thought a had to be like a real number.
Right. So this table is kind of incomplete. What it should really say is that the real part of a has to be greater than 0. Or sorry, greater than 0. Yeah.
So if the real part is greater than 0, then you treat the entire exponential
Yes.
as like your a.
Yes. Yeah. You'll see this again when you do Laplace transforms in controls, where we actually care about this. But for this one, yeah, I should have made it more clear. Any other questions? Right. Okay. So to clarify. Stay. Okay. All right. So let's just do the first term. So 1/2 e to the negative alpha plus j 2 pi f naught t. Right? And what I'm saying is that this looks like something similar to e to the negative a. You know what? This notation's going to be confusing. I'm going to change this alpha to beta. Right? It's different. Looks different from a. Alpha at us of t. If the real part of a is greater than, has to be where the real part of a is greater than 0. Right? And if this is true, then the Fourier transform looks like 1 over a plus j 2 pi f. So what is the real part? And we're going to say, OK, let a equals negative beta plus j 2 pi. Sorry, negative a equals negative beta plus j 2 pi f naught. Right? And we're also telling you that, does it say in the problem? Yeah, they say that that number is greater than 0. So beta, where beta is greater than 0. So real part of a is equal to b, which is greater than 0. So that checks out. That also means, to clarify, that means a is equal to beta minus j 2 pi f naught. Therefore, substituting back, we get 1/2 times the Fourier transform, which is 1 over a plus j 2 pi f. And we substitute in for a, which is beta minus j 2 pi f naught. And if we replace beta with alpha, which is what we originally had, alpha minus j 2 pi f naught. Oh, great. OK. So this is one example of using Fourier transform properties to do it. A useful technique that you'll should remember from high school or Calculus 2, if you took it here, is partial fraction decomposition. But I don't think people remember. This is partial fraction decomposition is especially important for the next half of the class. Sorry? Someone have a question? OK. So I'm going to go over an example that uses partial fraction decomposition, which is this problem here. So we're going to find the output y of t. Assuming that this system is LTI, we can do the convolution. So we want to find y of t using the Fourier transform method. So what our strategy is we're going to find the Fourier transform of y, and then do the inverse Fourier transform to get our y of t. Well, what is y of f? Y of f is just x of f times h of f. This is using the property, the convolution property, because y t is equal to x of t convolved with h of t. Right? So let's write this out. So we're going to take the Fourier transform on x of t. So x of t, x of f, the Fourier transform, right, using the table. It's a complex exponential, e to the negative at u s of t, where a is equal to 1. So it's just 1 over 1 plus j. I'm going to use omega, because it's just for simplified notation. But remember that omega is equal to 2 pi f. Cool. What about h of t? Well, notice that h of t is equal to e to the t us of negative t. And in the problem, x of t is equal to e to the negative t us of t. On our Fourier transform table, we have equation for this, right? E to the negative something. Here, we don't have e to the negative something. But you can also recognize that there's another property that wasn't on the table I showed you, but it is in the textbook, is that you can also reflect a signal, and there's associated property. But if you don't know that signal, you can recognize that h of t is really equal to x of negative t. Right? Because you replace this t with a negative t, that becomes positive. Replace this t with a negative t, becomes negative. So using that fact, we can then just say that the Fourier transform of h of t is 1 over 1 minus j omega. Right. Any questions? Yes.
Why did it, just because it was negative t, did it become 1 minus?
Yeah, so the property is called time reversal. So if x of negative t, the Fourier transform is just x of negative f.
On our homework, like a lot of times, like Fourier transform of like capital H, like x of j omega, or like h of j omega.
Yeah, so it's the same thing because it's just to save like for notation purposes. H of f is the same thing as h of j omega.
Like, I guess like so f in our place, like we use our property to be like the 2 pi f. Like
Yes.
that wouldn't be j. They aren't like interchangeable as like j omega though, right?
Right, so you can't just plug in 2 pi f directly because there's a difference in how their analysis and synthesis equations are written out. But you should be able to, if you actually derive it with the 2, you should end up with the same thing. I'm only doing this because it's just easier to write. But you could replace all the omegas here with 2 pi f, and this would still be valid.
Okay.
Yes.
So is j omega just I 2 pi f?
J omega is just j 2 pi f because omega is equal to 2 pi f. Yeah. People look confused. Right? Because we said earlier in the review session that omega is angular frequency. And angular frequency is just 2 pi times your frequency. So for this example, right, I said that x of f is equal to 1 over 1 plus j omega. In this case, you can't just replace omega with 2 pi f. So this is the same thing as writing 1 over 1 plus j 2 pi f. It is the same. Yeah. So what I said earlier was that h of t is really the reflection of x of t. Right? So that means the Fourier transform of